Good afternoon. I'm Kristen McCaleb. I'm the program manager for the Genomic Medicine Initiative at UCSF. Today, we're going to talk about how SciAps and UCSF are using software and genomics to transform the care of cancer patients. Approximately 75% of cancer patients will get a drug that is ineffective for them. Now, this isn't because the drugs themselves don't work. It's because we aren't matching the right drug with the right patient. Cancer patients used to be treated with what you could think of as a nuclear bomb style approach. They would receive a combination of chemotherapy, radiation, and surgery with little consideration for what their cancer looked like biologically. This one-size-fits-most approach resulted not only in a 75% failure rate, but in a lot of pain and suffering for the patients. At UCSF, we're leading a transformation in precision cancer care. We're using genetic data from each patient in order to find the right treatment for each of our patients. What is precision cancer care? Well, it begins with sequencing the genome of the patient's tumor. Then we compare the patient's medical history and their genetic markers against our institutional knowledge in order to try to identify a targeted therapy based on that patient's medical and genomic profile. But delivering precision medicine is no easy task. We have to provide actionable information based on very complex data to the doctor while overcoming our legacy software infrastructure. Now, in the medical world, our legacy software is the best of the 1980s. We have legacy systems for medical records, for imaging, labs, drug ordering, and drug administration. And all of these systems are silos. Furthermore, the workflow of precision medicine is complex. It is not automated. And there's no system for capturing the data and knowledge that's generated in order for us to learn and improve our quality of care. Furthermore, in order for our providers to deliver precision medicine, they have to rely on a combination of multiple tabs in the electronic medical record. There's still lots of paper and many Excel and PowerPoint files. One legacy system we have to overcome is our electronic medical record. EMRs are transactional systems built for billing and compliance. They cannot handle complex genomic data, and they do not enable data mining and visualization. However, the EMR is central to the doctor's workflow, so we have to interface with it rather than try to ignore it. One example of how our processes currently fail is around the security of genomic data, which is difficult to interpret and emotionally sensitive for the patients. If we don't want someone to blurt out a result before we've had a chance to counsel that patient, we just don't print out the PDF of the clinical report. Likewise, until we've talked to them, we don't fax it to the referring provider. And because patients can log in via a patient portal to the EMR to be able to see their data, until we've counseled them, we don't scan it into the EMR. We rely on these antiquated processes day in and day out. And As if this wasn't enough effort for all of our providers, once the data's in the EMR, it doesn't get a whole lot better. In order to find critical medical data, any provider has to go through an average of 23 separate steps in order to determine a patient's treatment plan. Genomic data in the EMR is not computable data. The genomic report is a PDF that is printed, faxed, scanned, and then imported into the EMR as a PDF or an image. So not only have we painstakingly converted a PDF back into a PDF, it's fuzzy and sometimes completely illegible. We have to do better. John.
Thank you. Thank you, Kristen. So, how do we fix this? My name is Jonathan Hirsch. I'm the founder and president of SciApps, and we've developed a software platform to enable precision medicine. So, there's a modern-day Tower of Babel within most medical centers. You have lots of different schemas, thousands of record types, millions of property types. There is really no standard terminology, and very frequently you have unstructured or semi-structured data, as Kristen was showing. And the tragedy of all this is that there's no reason for this to be the case. Genomic data was structured when it came off the instrument. It's the failure of the current IT systems that the genomic data winds up as a PDF. And on top of it, the fax machine is still the API for healthcare. It's still how data gets exchanged between systems. It's how a lab sends data to a medical center. It's how a referring physician sends data to a tertiary care facility like UCSF. This is still how data gets exchanged. So let's talk about the solution to these problems. So the first step of the solution is data integration. So you have to build a system where you're ingesting complex laboratory, genomic, and sequence data. You have to be able to do one-time migration of PDF, Excel, PowerPoint, and believe it or not, still FileMaker Pro databases. And you have to interface with the current systems in the medical center. So that might be an electronic medical record. Occasionally, there's a data warehouse. There are things called PACS systems that store images, CPOE, which does physician ordering, LIS systems in the pathology lab, and drug administration systems which control how the drug is actually dosed to the patient. So you have to integrate all these systems in such a way that the physician then has access to that data. So here's the second part of the solution, providing an easy-to-use visual dashboard for the clinician. Now, in the rest of the world, in the web world, in the enterprise software world, this isn't anything innovative. This is just standard par for the course. But in the medical world, they don't have anything like this. They don't have the ability to see clinical data, omics and genomics data, drug procurement, longitudinal information, imaging metadata. Bringing all this together is not currently possible in the medical system, and this is part of this solution. Furthermore, you have to enable the workflow. So workflows in medicine are incredibly complicated, involve a number of intricate steps, and sometimes have recursive processes that are really important to enable the learning process in healthcare. So in this case, the UCSF workflow is complex and multi-step, involving clinical workup, consenting the patient, ordering the test, getting the actual specimen and sequencing it. And this is actually the standard part of the process. The more complicated part of the process is downstream, involving taking all of the genomic variants in to a system and first of all, just databasing them. So right now, if you go and get your genome sequenced from a medical center because you have cancer, most of the time, that data is an Excel spreadsheet on some hard drive sitting somewhere. The concept of databasing critical information is still foreign in the medical system. So the first part is just databasing information. The second part is enabling the querying of that information and indexing that data. So right now, if you want to say, I want a patient who has a certain genetic alteration when they have breast cancer. You can't do that in any medical system. So that's part of the workflow that needs to be enabled. Then generating reports. Right now, reporting in the medical system is a manual process. Someone looks at a set of source data, they open up their Microsoft Word document, and they write a Word doc. And that's reporting. Now, we need to change that by providing automated reporting processes so that you don't have to spend so much time manually authoring, and you can actually create reporting in a meaningful, usable way that involves structured data. Once a report is generated, today the delivery mechanism is again via fax. Well, now let's replace that with a piece of software. Then you have group review processes called molecular tumor boards or clinical data review boards. Right now, a bunch of people get in a room with a presentation on the screen, they all talk, they walk out of the room, and the knowledge is not captured. So if you're a patient and you're being seen 3 months later, all of that knowledge has now disappeared. It's in the physician's head, maybe, or it's in one physician's head and another physician needs to go find the right physician to ask, and they need to go recall what that information was. So now let's replace that with a system that captures knowledge and that enables that knowledge to be used on an ongoing basis. And the final part of it is then capturing the actual decisions made. So decisions in healthcare are not captured. Not at all. The decision, again, remains in the physician's head. So let's capture that clinical decision, and let's enable the decision to be preserved into time, and let's enable that decision to be evaluated for efficacy. Because perhaps you can learn something by figuring out if your decisions were effective or not for the patient. So this is the new process that's being enabled, and this was all manual before. So what we at SciAps do is provide our enterprise software platform to enable these precision medicine processes. And there are 3 key aspects to it. So one is integrating molecular and genomic data into the clinical workflow. The second is tailoring decision support based on your organization's best practices. And the third is enabling the dissemination of this information across not just the individual clinicians within your hospital, but across your entire network. Because what happens in healthcare is you have centers of excellence that try to disseminate their knowledge throughout the broader healthcare world. And today, these processes are not enabled at all by software. So SciAps has been adopted by large healthcare providers. We're here today to talk about this in the context of UCSF, but SciAps has been adopted by a number of healthcare providers, both academic and community-based. So how do we get from data sources to clinicians? So the first part of it is the architecture for ingesting data. And we'll go over a high level of this and then start zooming into more technical details in a moment. So the high-level architecture is providing a semantic computing-enabled platform for reaching into the legacy systems and pulling out and integrating data. Now, we do this using a semantic computing platform because the data in the medical world is incredibly complicated. It has numbers of different file types and property types, as we were discussing before. And the data types require controlled vocabularies and other standardization. There is a high level of use of things like synonyms and hierarchies in the medical world that need to be enabled through a piece of software. We also do this because there is really no 2 set of systems in the medical world that practice medicine the same way. So you need to be able to configure how your application ingests data on a per-site basis, because UCSF and Stanford and Intermountain all practice medicine in slightly different ways. And of course, we'll talk about this more, but we have to have industry-leading security and HIPAA compliance. The next part is tools. So there's no point in integrating data if you can't do anything with it. The first set of tools are query tools. So today, if you go into a hospital and you're an oncologist and you want to say, how many breast cancer patients have I treated over the past 6 months? And how did they do? You cannot ask and answer those questions in the medical system. So the first thing we need to enable is querying of data so that the physician and the healthcare leaders can ask those questions. The second part is we then need to automate processes through rules. So if we're generating reports, decision support notifications, or any other high-volume mechanism of notification, we need to enable that through rules that are performant in real time. And all of this is happening in a clinical care context, so it needs to happen immediately. The next part is knowledge base. So we need to be able to store knowledge throughout the process. So we mentioned before that the physician's knowledge is never captured and reusable. And this system then allows the physician's knowledge to be put into a computable setting and disseminated across their network. And then the final bit is workflows. So complex workflows in the medical system for doing everything from the most basic report generation to figuring out how a patient's care is delivered over the course of time. Those are all complicated workflows that need to be enabled through automation. The final piece is then the applications on top of the system. So interactive reporting, patient dashboards, decision support notifications, and the ability for an analyst to query data and construct dashboards. Again, all of these features are things that would be common in most of the rest of the world, but are brand new to healthcare. And because the health system already has a number of legacy systems, integration is a key element. Now, saying REST APIs to people in the healthcare world is like speaking gibberish or jabberwocky. It does not make sense to them. So what we have to speak in terms of is interface engines, HL7 messaging, and other connection capabilities to be able to interact with the legacy software that they have. So now let's drill in a little bit more and talk about architecture on AWS. Now, to emphasize, we're not talking about running research on this system. We are talking about running clinical workflows where patients are seeing a physician and the application is being used to figure out the right treatment for that patient. So we are running real clinical workflows on this system. So the system has to be built in a highly redundant and highly performant fashion. And the system cannot go down. Cancer patients are being treated using this piece of software, and the data needs to be accessible to the clinician. So in many ways, to many of the people in this room, this will look like a standard web application architecture, and that's a good thing. But again, these are new concepts in the healthcare realm. So a few things that we do of note, and we're going to drill into a few more of these in detail. So we serve up a thick client web application. When you come into our system, we are deploying in a virtual private cloud setting, and we even go as far as provisioning dedicated hardware in the Amazon environment. Then we set up web servers, gateways, and interface engines in separate DMZs. And then when you come inside the SciOps customer deployment, what you'll see is in some ways, again, a standard web application. So there's a REST API, web application components, application data layer, and access layer. But then there's some stuff in there that is a little out of the ordinary. So you'll see Sparkle layer, semantic layer components, RDF biomedical data store. So what SciOps does is we actually store all of the medical data in our system in a semantic computing store or an RDF store. And that provides a highly structured and accurate way of working with medical data that also allows us to accommodate terminologies within the system that are critical for healthcare. The other part of this is that this is entirely configurable. So we've built out a system such that you can configure the semantic computing layer in real time within the application and have both the RDF biomedical data store and the web application components and user interfaces automatically manifest themselves based on your configuration of the RDF store. And then you'll see on the left-hand side of this diagram the fact that we are backing up via snapshots into S3, and we'll go through that in more detail too. But the critical element of this if you take home one thing from this, it's that Amazon enables enterprise-grade web applications, and it doesn't constrain our ability at SciAps to choose the most appropriate technologies for the job, while still enabling us to do this in a HIPAA-compliant manner. So here's some more of the technical aspects of the stack. So web application stack, single-page JavaScript, semantic data layer using a triple store that is very poorly named Big Data. It's a real thing. Look it up. Our deployments leverage the HIPAA covered services, or the BAA covered services, EC2, S3, and EBS. Our configuration facility, which is what I was talking about before, allows us to configure most of the components of the application ecosystem within Amazon. And then HL7 messaging, which we'll cover in a few slides. This is a critical element to enabling us to interface with the broader medical system. So in terms of why we use a semantic data platform running within our system on top of AWS. So it's really for these 5 key points. Medical data is incredibly complex, and you need to be able to capture the expressivity of the medical realm within your software. Flexibility. So as I mentioned before, no two medical systems practice medicine in the same way or even think about data in the same way. So you need to be able to configure that complex data system for that customer. Customization. Very frequently, people will want different interfaces, visualizations, et cetera, and you need to be able to have customized hooks for that. Integration. Semantic computing enables effective integration of multiple data types. And precision, very exact queries, which is really what drives a lot of the rules capability within our system. Of course, we use Amazon for its high availability. And while this is critical in enabling me to stream my Netflix movies as I'm flying coast to coast on airplanes, it really does help in the medical world. So in the medical world, you might have physicians logging in from different physical locations. You might have lots of data that's scaling up very, very rapidly as sequencers are running and depositing data and as patients are coming in and being seen. And you need to be able to deal with all of this traffic coming in. And this, again, is nothing new to those of you who use Amazon, but is something that's totally foreign in the medical world. So the high availability enables really high-quality medical-grade applications. Geographic distribution. So UCSF is located in San Francisco, but they actually have a number of different locations. So they have 3 campuses, 19 other clinics and locations, and 5 affiliates. So UCSF is geographically distributed within their region, but they also have sequencing performed at UCLA in Los Angeles, and they have other molecular testing being performed at laboratories around the country. So regardless of where the medical system is based, they always have a complex geographically distributed landscape of data sources. And those data sources need to be integrated within the system at UCSF. Now that's a perfect argument for using cloud computing, because what we can do is co-locate or locate the servers nearest to where the data is, get the data streamed into our system on Amazon, and then use Amazon's facilities for routing data between their different regions. And we make heavy use of that in order to enable the effective transfer of high-volume genomic data between different sites. And just for a level set, when you're talking about a genome, you might be talking about 100 gigs for one single patient. And if you're talking about other molecular information, you're talking about an equivalent size, but changing over time. So if you're doing a molecular profile of a patient several times over the course of a few months, it's really critical to be able to deal with this high volume data. Now, how things used to be done and how things are still done in many cases is drop shipping hard drives. And this is still a mechanism that's used all over the medical world. And some people don't even like to use FedEx. Some people get in their cars and drive from one side of town to the other. Segregation of production dev and QC. So again, this might seem like something that is par for the course for many of you, but it's something that is very critical in the healthcare world because frequently testing in the healthcare world of software is actually done manually. So you will actually have manual user acceptance testing where people are logging into a development instance of their EMR, triggering a test order, and then we have to test that it's received on our side. And we need segregated but mirrored production dev and QC environments to enable this. So we set this up very easily using CloudFormation and other Amazon tools, and it makes it incredibly easy to reduce the burden on the SciAps side of setting up all these different segregated environments. And of course, setting up pipes to mirror the configuration is again very easy using the Amazon tool sets. So secure integration with customer systems is one of the most important points in building a healthcare application. On the right side, you'll see your typical hospital. They have their computers, they have their medical record, their pathology systems, other systems. Within the hospital firewall, this is always floating around unencrypted. So patient data is moving between hospital systems unencrypted. Once you get inside the firewall, everything is free and open. Now, clearly this is not the best way to practice, and we need to one-up this when we go and present to a hospital. So if you look at the left side, which is the SciAps customer deployment, once you get inside our VPC in the Amazon firewall, everything is encrypted. Everything is encrypted at rest, and everything is encrypted in transit between all components of the SciAps application ecosystem. Because we want to go to the hospital and say to the hospital that our security built on Amazon is actually a little bit better than yours. And that you can trust putting data inside SciAps software on Amazon. Now, if you look at the bottom and you see the IPsec tunnel, what is that and why are we using it? So HL7 messaging is one of the interface languages that's used in healthcare. Think about it as a glorified XML file where there isn't a lot of standardization and people can kind of put in it whatever they want. That's HL7. But HL7 is used by a lot of people in healthcare. So you need to be able to work with HL7 messaging. However, HL7, the most popular versions deployed, are actually insecure and unencrypted. So what you have to do is then set up your IPsec tunnel between your firewall on Amazon and the customer, the hospital's firewall. Now, what we did at SciAps is we actually deployed our own gateway solution using open source technology. And the reason that we did that is that we wanted to encrypt the data flowing out of our gateway into our own HL7 interface engine. And what Amazon provides is the flexibility for us to implement our own version of best practices within the Amazon ecosystem. Once it flows, once the data flows from the gateway into the interface engine, again, encrypted, the interface engine turns it from HL7 into properly structured data that we can work with. And then again, it's encrypted to go over to the SciAps application. You might be wondering what SciMessage is. This is actually a lightweight messaging integration service that we have built at SciAps that provides high ability to deal with incoming messages and provides the ability to do things like error handling very, very well, because the data flowing in that bottom line is all patient data, and we need to make sure that we never drop a message, never ever drop a message. So this messaging facility that we created provides high levels of confidence that we will never drop a message within our system. Real-time computation. Once you get the data in, then what is the physician doing with it? So the physician is actually sitting with the patient, or they're sitting in their office, and they're accessing gigabytes and gigabytes of complex genomic data. And they want to be able to say, what is the most critical data that I need to make a treatment decision for my patient? So they need point-of-care access to large-scale data. but we also need to be able to implement a rules-based infrastructure for determining the correct data to surface to that physician at any given point in time. So yes, they should be able to access ad hoc data, but we should also be able to automatically surface relevant data. And you can't do this by just predetermining the data that they'll need, because the facts on the ground, the situation changes frequently. So you need to be able to have the physician see a patient and have the relevant data surface at that exact point in time, not the relevant data from last night. Now, how we build this is using fast complex queries and a semantic rules engine, because the semantic rules engine actually enables real-time access to data. However, this is incredibly memory intensive, We index everything and put all the indexes in memory, and the indexes represent all of the data in the application. So we could not do this on any other system aside from Amazon. Amazon enables us to have a really high memory intensive application. So all of the data is also indexed in real time, again, computationally intensive. And we have to run these things 24/7. So it's not like you could just spin this up, bring it up for a specific point in time, and then spin something down. You actually have to have this available 24/7, because you never know when that cancer patient is going to come into the emergency room and the oncologist is going to get a call. So you need to have these applications available consistently. And of course, Amazon provides flexible node size, number, and moving indices between nodes. So we're able to spin up whatever number of nodes we need. We're able to distribute this over the nodes at Amazon, and we're able to run the application in a highly performant fashion. Now, HIPAA compliance, which is the big topic du jour. One of the critical elements of HIPAA compliance is backup, recovery, and redundancy. We are almost always asked by medical systems, what's the physical location of your backup tapes? Always, always. And we have to explain to them that no, we actually don't use backup tapes, that we can achieve backup, recovery, and redundancy through Amazon's capabilities. So how we specifically implement this is we have our customer instances running, and we take nightly snapshots using Amazon functionality, EBS, and the like. And we actually take those nightly snapshots and we back them up to the specific region in which the customer instances are running. And because of Amazon S3's capabilities, these backups are spread redundantly across different availability zones within the regions. And I don't know what number of nines S3 is architected to, but it's a lot better than your backup tape. So that's the first element. Now, as all of you know, Amazon does not take your data from one region and move it to another region. And that's one of the critical elements of enabling HIPAA compliance that we'll get to. But we at SciAps do want to take backups and have them living in a different region within the United States. So we actually will then mirror our backups to different regions. And we test our backup recovery facilities on a practically daily basis. And our max time for getting a customer up and running after any sort of failure is actually 1 hour. We can have a full recovery of the system within 1 hour. Now again, compared to most of the rest of the medical system, this is a really short amount of time. The other component is failover. So we're actually running redundant customer instances within different availability zones of Amazon. So if an availability zone goes down, we are okay. Now again, in the earthquake-prone region of California, where UCSF is, try doing that in your medical center basement deployed data center, which is the state of the art today. So let's talk about security. So of course, Amazon has standard security. FedRAMP, ISO 27001, and SOC 2, and all of the other logos that you're familiar with. And of course, we have web application security, single sign-on, etc. And the data center security from Amazon is best in class. Now let's go one above and talk about healthcare grade security. So the first thing that Amazon enables is customer data segregation. So SciOps does single tenant deployments for each and every hospital customer we have. The reason that we do this is because single tenant deployments actually enable the hospital to feel much more comfortable that their data is not being commingled with data from other hospitals. And this is very important for the hospital in terms of controlling their regulatory environment. It gives the hospital peace of mind. We also go so far as running dedicated hardware on Amazon. And CloudFormation templating makes this really easy, because I'm sure if I went over to the Netflix session, they would be gasping in horror that we do single tenancy and dedicated hardware. But CloudFormation templating makes this very simple and makes it such that we can run this with minimal staff on our side. And of course, Amazon provides a management console, which makes this very easy to use. So we talked about data encryption before. We encrypt all data at rest and in transit, including in transit between all layers of our application, which is a far departure from what the medical system typically does. And we use Amazon Virtual Private Cloud technology and their firewall, and we provide gateways between the Amazon firewall and our customers' firewalls. So HIPAA compliance, Amazon has a set of covered services, EC2, S3, EBS, Glacier, and I heard that one more was added this morning, or yesterday. And what I'm here to tell you is that you can build a high-quality, enterprise-grade web application using a small number of these dedicated services. So this is not representative of the full functionality that Amazon offers, but you can create a high-quality application using these small number of services. And then the AWS platform provides HIPAA-critical functionality like access logging, monitoring of data integrity. But again, most importantly, it doesn't constrain SciOps in the choices that we make to add further security, like encrypting of data in transit between layers. Now, part of HIPAA compliance is that your data does not leave the United States. So Amazon provides the ability to segregate data within an AWS region, and AWS doesn't move data between one region and another. So what that lets SciOps do is SciOps can assure our hospital customers that their data will not leave the United States. If we work with a hospital abroad, we can assure the hospital that their data won't leave the European region or the Asia region. And again, that's a critical element of HIPAA compliance. And of course, the final element of HIPAA compliance is the business associates agreement. So we're very happy to be able to say that SciOps and Amazon have a business associates agreement in place, and that BAA provides a high degree of coverage, and the BAA has enabled us to pass InfoSec reviews with some of the largest hospital systems in the United States, not just UCSF, but many others as well. So that's how SciOps is enabling an enterprise-grade application on top of AWS in the healthcare realm. And with that, I'm going to turn it over to Nate Slater, who's a AWS solutions architect specializing in healthcare. Nate.
The importance of helping customers like UCSF and SciOps deliver on the promise of precision medicine can't be understated. I'm probably not the only one in this room, unfortunately, who has had firsthand experience with the current state of affairs in cancer treatment today. I lost my mother to uterine cancer in 2011 after she had endured several brutal rounds of chemotherapy, each one less effective than the previous. She was receiving medical care from some of the best in the world, and yet at times it felt like nobody really knew how well the treatments were going to perform, or not perform in her case. We at AWS are very excited to have partnered with UCSF and SciOps and help them deliver on the promise of precision medicine. The targeted treatment of cancer based on a patient's tumor biology and medical history has tremendous potential to improve treatment outcomes as well as the quality of life for millions of cancer patients around the world. At AWS, we feel very strongly that our customers should focus their energies on the functionality of their applications, not the undifferentiated heavy lifting of managing IT infrastructure. We also feel strongly that our success is predicated on security being our top priority. Our shared responsibility approach to security provides world-class security measures from the physical data centers to the hypervisor, allowing our customers to focus on building their applications in a highly secure manner. As we've seen today, by leveraging both the rich ecosystem of AWS services and the shared responsibility security model, our customers, like PsyOps and UCSF, can focus instead on devising solutions to the really hard problems in their domains. So we're honored to be part of this truly innovative and novel approach to personalized medicine and the positive impact this will have on those suffering from cancer. Thank you.
All right. With that, I want to thank everyone for coming today. I especially want to thank our partners at Amazon for making this all possible and for providing the best infrastructure to run your healthcare applications on. If you have any questions, myself, Kristen, my CTO, Tony, and our VP of Customer Solutions, Andreas, we will be outside and in the meeting room. If you have any questions about how to build a HIPAA-compliant application on Amazon, we're more than happy to answer your questions. Thank you so much for coming today.